Good afternoon, everyone. I'm Tomiko Brown-Nagin, Dean of the Harvard Radcliffe Institute. It's my pleasure to welcome you to our annual Kim and Judy Davis Dean's Lecture in the Sciences. Today, our program will explore the science, technology, and people behind the groundbreaking field of gravitational wave astrophysics. And we're honored to be joined by the distinguished astrophysicist, Nergis Mavalvala. Before we begin, I want to take a moment to acknowledge Kim and Judy Davis, whose support makes this lecture series possible. I also want to thank the members of the Radcliffe Institute Leadership Society and all our annual donors. Your generosity keeps Radcliffe programming free and open to the public, and we thank you. Back in the early 1960s, NASA's Project Mercury made history by putting the first American astronauts into space. Shortly before his mission, one of those early astronauts received a letter from his father, who predicted the flight would bring his son fulfillment, not because of fame and glory, but because of the discovery of new knowledge. This experience, his father wrote, is a precious thing. It is known to all researchers in whatever field of endeavor who have ventured into the unknown and have discovered new truths. Indeed, our desire for new and deeper understanding has driven path-breaking discoveries throughout history, and few subjects have captured our curiosity more than the cosmos itself. Our ideas and questions about the universe inspire art, affect policy, influence culture, and of course, motivate some of the most cutting-edge scientific inquiry. Over centuries, scientific discoveries have dramatically reshaped our understanding of the universe and where we fit into it. One such discovery came quite recently. In 2015, for the very first time, scientists observed gravitational waves using the Laser Interferometer Gravitational Wave Observatory, or LIGO. These ripples in space-time had been predicted some 100 years earlier in Einstein's theory of general relativity, but they had never been observed, in part because we lacked instruments sensitive enough to make the exacting measurements required. So the detection of gravitational waves was a triumph of both theory and technology, and its significance is difficult to overstate. Three of the creators of LIGO won the Nobel Prize in Physics in 2017 for their discovery. And gravitational waves are more than a cosmic curiosity. They give us an entirely new method for studying the universe. Traditional observational instruments like telescopes rely on light, and they encounter fundamental limitations in the expanses of what Nergis has called our dark and warped universe. Gravitational waves are now allowing us to study the universe in ways that were impossible just a few years ago, and they've already contributed to significant findings, such as the merger of black holes and the cosmic origins of heavy elements like gold. And this is only the beginning. Far more discovery lies ahead. And who better to help us understand these exciting possibilities than Nergis Mavalvala? Nergis is a longtime member of the LIGO team that first detected gravitational waves, and she applies quantum mechanics to improve the sensitivity of the LIGO instruments. And for perspective, these instruments are making measurements that are orders of magnitude smaller than a proton. Nergis is dean of the MIT School of Science and the Curtis 1963 and Kathleen Marble Professor of Astrophysics, and her research lies at the intersection of two fields that are often in tension: quantum mechanics and general relativity. She has received numerous honors and awards, including the LGBTQ+ Scientist of the Year in 2015, and the Special Breakthrough Prize in Fundamental Physics as part of the LIGO team in 2015. She is a 2010 MacArthur Fellow and a member of the National Academy of Sciences. After Nergis's remarks, she'll be joined in conversation by my colleague, Edo Berger. Edo is professor of astronomy at Harvard and serves as co-director of the science program here at Radcliffe, where he was also the 2019-2020 Mildred Lunda Weissman Fellow. Now, I mentioned that gravitational waves have helped scientists study the cosmic origins of heavy elements. Edo is a leader in this research, and it was the focus of his fellowship here at Radcliffe. Following Nergis and Edo's discussion, we'll turn to audience questions. You can use the Q&A feature on Zoom to submit your questions at any point during the program. We only ask that you keep your questions brief so we can address as many of them as possible. With that, let's begin. Welcome, Nergis. The floor is yours.
Thank you so much, Tamika. What an eloquent introduction to gravitational waves, and an all too generous introduction for myself. So it's a real pleasure to be here. I will mention one other thing that I think makes this an especially auspicious day, which is that it is today to the day 6 years ago that first signal from the distant universe came to us by way of gravitational waves. So I'm very pleased to be here with you today. So I'm going to just take a quick second to share my screen, and I'm going to tell you a story. And that's really how you have to sort of see my remarks today. They are a story about a discovery that took place, as we said, starting with the discovery 6 years ago, but the story actually harks back to over a century ago. The story is about opening a new window into the universe, and the protagonist is gravitational waves, and there'll be many other human protagonists along the way as well. But before I can tell you about a new window into the universe, we really have to consider what was the old window into the universe. And the old window into the universe was light. And for millennia, humans have pondered the mysteries of what's out there in the sky. And the messenger has always been light. And light, it's a natural messenger. It's what our eyes perceive, and not just all light, but just the optical part of all possible colors of light. And indeed, from using the power of our own eyes to see, a paradigm shift in observing the universe came in 1601 with Galileo, who we believe was the first person to point an instrument at the sky, a telescope. And since the time of Galileo, we have really expanded our capabilities to look towards the skies through increasingly more powerful telescopes of different colors. This is the Giant Magellan Telescope that is to be built in Chile. That will be the largest telescope ever to be built here on the Earth when it's completed, competing with another kind of telescope. And what have these telescopes, these sophisticated instruments, told us? Well, they've told us that these little patches of starlight are much more complex story of the universe. And this is one of my favorite astronomy pictures. It's actually a picture of an object called Cassiopeia A. And what it is it's actually a remnant of a supernova. And so the beauty of this picture lies in a number of things. The one is all these different colors that you see are different colors of light that our eyes couldn't even see. For example, the blues and purples are actually X-ray emission. The reds are infrared emission. But when you put all of these different colors of light together using different arrays of telescopes, you can put together the story of this star. So the story of this star was, it was a star not too different from our own sun. It was pretty much like our own sun. And at some point, this star, like many stars, kind of ran out of the nuclear fuel that makes it shine and give off light. And when that light source turned off, the gravity of the star kind of pulled it on itself, and it sort of implodes. And in that sort of collapse of the star, it gives a shell of material, and that's what you see, all the surrounding material. And if you look really carefully at the very center of this picture, you see a little blue dot. And this little blue dot is the new star that was born when this parent star died. And in this particular instance, it was an object called a neutron star, and it's called a neutron star because it's made up of neutrons. And we'll come back to these neutron stars. Now, if this parent star had been a bit heavier, this one was likely to be about the mass of our sun, or maybe 2 times the mass of our sun. If it had been 5 or times the mass of our sun or heavier, the gravity of that star would have continued to cause it to collapse, and it would have collapsed into a black hole. And so that's the story of this star. Now, a black hole is, as its name would suggest, black. It has so much gravity packed into such a small volume that it gives off no light. If I were very accurate, I'd say it gives off almost no light. And therefore, we have no means of observing objects like black holes that do not give off light. And yet we know that these are one of the most fundamental building blocks of our universe. So how might we study them? And the answer to that question was first proposed to us by Albert Einstein in 1915 and 1916 as part of his general relativity theory. And Einstein's general relativity theory told us many, many different amazing, mind-blowing things about space and time. But one of the less well-known features of general relativity theory that Einstein told us was that space-time doesn't just warp. You've famously seen these pictures of funnels under black holes or stars, but that the space-time also ripples. And these ripples of space-time, these gravitational waves, actually carry away energy. So here is a cartoon of 2 neutron stars. They're orbiting each other. And as they orbit each other, they're losing energy to these gravitational waves, which are literally the surface of space-time itself rippling and carrying away energy. And as that energy is carried away, these 2 neutron stars would get closer and closer together, and eventually they would collide. And this all comes to us right out of Einstein's theory, even though he himself was very skeptical about what the math that he came up with was telling us about the universe. But that's a story for another time. So what are these gravitational waves? So as early as 1916, in one of his earliest papers, Einstein dismissed them as being too faint to ever be useful. Now we fast forward after many, many iterations of thinking through these objects to the early 1970s, late 1960s and early 1970s. And the timing of that is very important because right around in the late 1960s, the first neutron stars were observed, even though they had been theorized as early as the 1930s. And this sort of set off a ripple of people thinking about what might gravitational waves look like from these neutron stars and black holes, and could they ever be detectable? So Einstein dismissed them as too faint to be seen. And this man, Kip Thorne, then a faculty member at Caltech, agreed with Einstein. He said, "Yep, they're pretty faint, but if you don't use ordinary stars, but you think about the gravitational waves emitted by the orbits and collisions of neutron stars or black holes, which are much more compact for the same mass, you might be able to." Kip Thorne calculated that these would have an emission of gravitational waves. The amplitude of that wave would be 10 to the minus 21. And I'm putting that number out a little bit tongue in cheek because it doesn't mean a lot until I contextualize what it is. And that comes from around the same time, also in the late 1960s and 1970s, Ray Weiss at MIT was an experimentalist and thinking about how might one detect gravitational waves. And he understood that if you could measure changes in distance of 10 to the minus 18 meters, now recall that is about 1,000 times smaller than the radius of a single proton. But if you could measure those distances at that scale, then you would measure the passing of a gravitational wave here on the Earth. Thorne and Weiss met in 1975, and they conjured up this idea of LIGO. And LIGO became a reality in the 20 years that sort of followed. In the 1980s, it was designed, and in the 1990s, it was built. And indeed, their ideas gave birth to a global network of such detectors. And these are aerial views of all these detectors. On the left here are the 2 US detectors, which are LIGO. these are aerial views because each of these detectors are kilometers long. And the principle here is that you have a laser beam that goes down any one of these arms, these tunnels, and points to a mirror, in the case of LIGO, 4 kilometers or 2.5 miles away. That mirror reflects the laser light back towards the laser. And if you had a really precise clock, you measure the light travel time. If a gravitational wave comes through, that light travel time would change because the gravitational wave is shrinking and stretching the space between the laser and the mirror. That's the principle. And then there's an enormous amount of technology that allows us to reach that precision of 1,000 times smaller than a single proton, or 10 to the minus 18 meters. And all of these ideas were laid out in a seminal paper by Weiss in 1972. And then it took 2 generations to implement these ideas and refine them until in 2015, on September 14, 2015, the first signals were captured by LIGO. And this is what they looked like. So this is the signature of 2 black holes colliding. And remarkably, what you see is on this plot, you see a set of bumps and wiggles. So there's a few things that are really amazing about these bumps and wiggles. I hope at the end of this lecture, you will never ever see bumps and wiggles in the same way, because every bit of bump and wiggle tells you a little piece of a story. So on the horizontal axis is time. And so we measured the last 200 milliseconds of the lifetime of these 2 black holes as they orbited each other, and the last 200 milliseconds before they crashed into each other. The vertical scale is even more amazing. This is the amplitude of the wave, the gravitational wave, and you see 2 things. So at the moment that the 2 black holes collided, which is the maximum of the signal, the wave had an amplitude of 10 to the minus 21. And if you convert that into how much were the mirrors of LIGO moving, that's 10 to the minus 18 meters. So enormous check mark for Kip Thorne. He told us in the late 1960s and 1970s, the wave will be about 10 to the minus 21 big. Ray Weiss told us how to make such a measurement, convert that wave into a motion that's 10 to the minus 18 meters. And here we had seen this. Now, what is the story that these bumps and wiggles actually tell us? So it's the story of 2 black holes. So once upon a time, there were 1.3 billion years ago, there existed 2 black holes. And these black holes orbited each other, giving off gravitational waves, just as Einstein's equations had instructed them to do. So here they are orbiting each other, and because they're giving off these gravitational waves that are carrying away energy, their orbit shrinks. They get closer and closer to each other, and they are distorting the space-time around themselves as they do that. And you can see in this particular movie, these 2 black holes were in a star field. So you can see how they distort the star field. They collide with each other, and they form a single black hole. So I'll play that movie one more time so you can see how the star field is distorting around. This is actually space-time itself being distorted by the enormous gravity of these 2 objects. They orbit each other, they get closer and closer together. As they get closer and closer to each other, the space-time gets more and more distorted, and they eventually form a single black hole at the end of this collision. Now, from the bumps and wiggles, the size, the times, and the number of bumps and wiggles we could see, you can reconstruct an enormous amount of information about the system. So we learned that the 2 parent black holes were about 30 times the mass of our sun. So they're really big, heavy black holes. Now, remarkably, and this blows my mind every time I think about it, and I think about it a lot, when these 2 black holes collided, the moment of their collision, they were moving at half the speed of light. So this is something incredible to contemplate here on the Earth, when scientists, physicists can accelerate electrons, light, puny electrons, to a fraction of the speed of light, and takes all our effort to do so. And nature can take these 30 times the mass of our sun objects and catapult them at half the speed of light. This incredibly powerful event. Now, we could also tell from those bumps and wiggles in the signal that these black holes were 1.3 billion light years away from here, the Earth. And then remarkably, we could tell that this new black hole that was formed was 3 times the mass of our sun lighter than the two parents put together. And I remember mass and energy, Einstein taught us are interchangeable. So when we talk about their difference in mass, we're also saying how much energy was released. And so what we can say is that in this collision, 3 times the mass of our sun was released in gravitational waves. And this was then observed to be the most powerful release of energy that we know of since the Big Bang. Now, there is one other piece to this story, which is that we know that the two parent black holes did not live happily ever after. They were destroyed to give birth to their child, this new black hole, very much as human parents do. We give up our lives to create lives for our children. Now, for this discovery, the founding fathers were awarded the 2017 Nobel Prize in Physics, and the Nobel Committee called it a discovery that shook the world. And I hope you see the playfulness and in that terminology, because indeed, when those gravitational waves passed through the Earth, ever so imperceptibly, they did shake our world. And yet we had these LIGO instruments that were precise enough to be able to measure that truly tiny thousandth of a proton length scale change and make the measurement. The story didn't end there. That was really just the beginning. Remember, I've told you we're opening a new window into the universe, and it would be a rather crummy window if all you could see was one pair of black holes that collided. Well, I shouldn't say crummy. It would have been a spectacular view, but now we're spoiled because we've seen more things as well. So fast forward now 2 years later to August 17, 2017, and for the first time, LIGO observed the collision of two neutron stars. And that's shown in this funny plot here, the blue and green plot, where on the horizontal axis we have time, and on the vertical axis we have the frequency of the wave. And what we see is that as time goes by, the frequency of the wave is increasing. And in fact, if you were to take this kind of time frequency plot and try to sing it out to yourself, it would sound like a chirp. It would sound like the chirp of a bird. It would sound something like whoop. So it's going from low frequencies to high frequencies and getting louder as well. And we knew when we saw this that this was not black holes because of the time scale. Remember, the black hole time scale was a fraction of a second. And now this signal was lasting over a minute in our detection band. So we knew these were very light objects, not heavy black holes, but lighter objects with very likely to be neutron stars, which are the lighter cousins of black holes. If a typically neutron stars are in the 1 to 2 solar mass range, and then black holes are usually 5 solar masses and higher. Shortly after LIGO saw its signal, 1.7 seconds after LIGO saw its signal, a signal was picked up by a gamma ray telescope, the Fermi at the Fermi Observatory, which is a space observatory that looks at gamma rays. Now, gamma rays are highly energetic. They're the most energetic form of light that we know. And so the question was, were these two events related to each other? Now, using the observations from LIGO and its sister observatory in Europe, Virgo, we were able to localize that this collision, whatever it was, weren't sure what it was. From the gravitational wave data, it looked like it was the collision of two neutron stars. We could localize where in the sky it was. And now there's another very important difference between black holes and neutron stars. Well, among other things, black holes are black. They don't give off light. Neutron stars are made of neutrons, and when they collide, they should be accompanied by a spectacular light show. When this observation was made by LIGO and a couple of seconds later by Fermi, we localized that this object should be visible from the southern hemisphere. But when we made the detection with gravitational waves, because we don't rely on light, you can also observe during the daytime. And so it was daytime in the southern hemisphere when we made this observation. And we sent out an alert to our astronomer friends, and my colleague Edo Berger, who will be joining us shortly, was part of the teams that went chasing after this object. And it's a little bit like tornado chasing or any other kind of chase that you have. There's high stakes, very little bit of time to prepare and get it done, and under difficult conditions. So about 11 hours later, a whole host of telescopes in the southern hemisphere pointed to that patch of sky that was identified by LIGO and Virgo as being the place where this object should be. And this is what I would call an astronomer's night to remember. This host of telescopes pointed to the sky. It's a very busy plot, but I want to just point you to a few things. Over here, you see there's GW for gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, radio. In all these different colors of light, telescopes pointed at the sky that night and for many, many nights to follow. And in every instance, they saw an object that was noteworthy. And I'll point you just to one data. So DECAM here is Edo's telescope, but I'll point you to the telescope DLT-40. And these are all images of the same galaxy, NGC 4993. And if you look at every one of these different telescopes from different groups, they all have a crosshair, and at the 11 o'clock mark from the galaxy, there is an object in the crosshair. And here is a zoom in from DLT-40, where 20 and a half days earlier in the crosshair, there ain't nothing. It's just another piece of sky. And this was, this told astronomers that a new object had lit up in the sky. And indeed, this is what we expect. These two neutron stars, whilst they were orbiting each other, they don't give off light. That's measurable. They're actually giving off gravitational waves. And those gravitational waves were observed by LIGO. And then when they collided, this was the light show that was seen by all the telescopes. So I'll give you I'll show you a sort of a very artistic and dramatic rendition of what that should look like in this movie. Two neutron stars orbit each other, and this time the white is the gravitational wave. They're only giving off these blue-white gravitational waves that are ripples of space-time. When they collide, as it is the light show, first the purples and the blues are the gamma rays, and then all of the light and the reds, which are the optical and infrared radiation that was eventually seen by telescopes here on the Earth, like the ones that Edo used. And that's the story of these gravitational. Now, I want to sort of end up by just telling you very quickly why this is important. This isn't a stamp collecting business. You're not just going out and saying, oh, I saw a black hole collide. Oh, I saw a neutron star collide. When you look carefully at the light from those neutron stars, you can look at the different colors of light, which is what's shown on this plot. And each of these peaks, each of these bumps and wiggles is telling you about the formation of elements in our periodic table. And in particular, this discovery solved an ancient conundrum here on the Earth, which is that we have too much gold. You might say, what a ridiculous statement, too much gold. Entire civilizations have been lost and won over gold. How can there be too much? But speaking from sort of a truly astrophysical record, we have more gold than we know where it came from, because our own star, the sun, doesn't make heavy elements like the gold in the abundance that we see. So we have long thought that gold must be made in these collisions of neutron stars, where you have lots of neutrons to fuse together heavy elements. And indeed, that's what that data showed us. So for the first time, we have understood and observed, if you will, where the gold here on the Earth comes from. So I'm going to sort of conclude by just telling you that we have a brilliantly dark and warped future ahead of us. Already with these discoveries and many more, we are answering new questions. We're improving the sensitivity of our detectors. We're also looking at putting such detectors in space. And I just want to say that this is how we are launching a new era of gravitational astrophysics. These are the first detections of direct observations of these gravitational waves that Einstein told us about 100 years ago. It took us 100 years to detect them because they're pretty darn faint. We've confirmed Einstein's theory of general relativity. We have seen neutron stars and black holes collide. And I, as someone who has worked my entire career on building the instrument that was sensitive enough to make such detection, it's really nice that the goddamn machine works as well at the sub-atometer precision that was needed. But I will tell you, we've turned on this completely new way to sense the universe. But this moment in history won't be remembered for these particular discoveries, but for the paradigm shift where we can now use gravity alone or gravity with light as a new tool for unimagined discoveries. So we have this new window into the universe, and it promises a really brilliantly dark and warped future. So thank you for listening. And it's also, I'm going to stop my screen share. It's a great pleasure for me to also invite Edo Berger to join us for a conversation. So welcome, Edo, and I will stop sharing my screen.
Thank you so much, Nergis, for such a wonderful talk and for taking us through the incredible history and amazing science of LIGO. It's truly inspiring to think about science that combines the smallest imaginable scales, much smaller measurements, much smaller than the size of a proton, and then it combines that with the largest possible scales, black holes in the far reaches of the universe. With this in mind, I would like to ask you a few questions before we switch over to questions from the audience. And I would like to proceed in a similar way to the arc of your talk, from the history of the field to what promises to be a really bright future. And I want to ask you both about your own personal experiences and the field in general. So let's jump a little bit back into the past. LIGO is an immensely complex scientific experiment that took several decades from conception to operation. In your opinion, what made this work? What ensured that LIGO will succeed? And what can we learn about this or from this about the future of big scientific projects in general?
Yeah, so that's actually a profound question, and one that I think this story tells really well, right? So Einstein tells us 100 years ago, there's these gravitational waves, kind of useless. But then the arc of scientific discovery inexorably brought us to confronting that these gravitational waves could be detectable once the discovery of neutron stars and black holes were made. And those discoveries, by the way, were made using just light around that's given off by these objects, but not all black holes would give off light. And so the important part of the story is that the technology also had to come together. So what happened in the 1970s that was so important? First was the discovery of black holes and neutron stars that made the astrophysics imperative. In 1960, the laser was invented, and that made this precision optical measurement possible. The L in LIGO stands for laser. It is the light source that made it possible. So a way to think about this is when you're trying to make such a precise measurement, you need a really, really good ruler. And the laser, the wavelength of the laser light is so stable that it can form a good enough ruler. So the technology came together, and then a third piece had to come together, which was actually more to do with political will. So this was a time when big experiments with long horizons were still possible to do. And the National Science Foundation, for example, has partnered, starting with Weiss and Thorne in 1975, has partnered with LIGO for decades before the discoveries were made. Now, I want to say one other thing that's a common misconception. So even for someone like me who worked in the field starting as a graduate student with Ray Weiss for 25 years before the discovery came, it wasn't like in those times it was all darkness. We were making progress, and that was essential for a funding agency to continue to fund you, for smart people to join your enterprise. And so we were publishing papers, we were showing that you were getting closer and closer to the goal, both from the instrument side and also refining the theory, the astrophysics, the data analysis. So all of those things had to come together, and they did. And I'll say one last thing. I think for something like this to work, you also needed inspiring leaders. And I think people like Thorne and Weiss were just that, because when I joined this thing in the 1990s, we were kind of a rat ragtag band of mavericks, right? No one believed it would work. And so they had to have both the vision and sort of the leadership to bring us along. So
no, thank you for that. And so now kind of a question more about your own experience with that. Can you share with us, or do you recall kind of specific moments when you thought, aha, this is really going to work, or, oh no, how are we ever going to pull this off?
So I would say most of the time, I didn't worry too much about, is this really going to work or is this not going to? Because then you'd never get out of bed and go into the lab the next day. Most of the time we were thinking in increments of milestones. We had to get to this level of making a measurement at the level of 10 to the minus 18 meters, for me, from the instrument side. And when I started in the field, we were at least on the order of 1 million away from where we needed to be. And so every year was kind of a factor of 10, you can think of it. It wasn't that, when are we going to get to that? So that was the first thing. And then the second thing was, I think for me personally, I think the precision of the instrument and the things that it has spawned, which it has done in its own right, it has spawned other areas of precision measurement, in itself was at least as beautiful as the astrophysical story. And because it has made us confront the smallest, most fundamental forces in nature at the quantum level. And so again, I think it was always this twofold thing. We're building an instrument that's never been built at this precision before, and we're going to make an observation that's never been observed before. And together, I mean, how could you say no? I mean, I got out of bed almost every morning just saying, this is the reason, I mean, pinch me someone, this is the dream. But then, can I answer one other thing? So then, September 2015 came the signal that I showed you, the bumps and wiggles that I hope everyone will learn to love as much as I have. And I and most of my colleagues, when we first saw that signal, we just kind of shook our head and said, "No, that can't be real." And in some ways, that's because we had so many decades without signal, but in other ways, that's exactly what every scientist should do. The moment you see something that you've been waiting for longingly, you should be skeptical. Is this real? Is your instrument tricking you? Is there something else going on? Or is this really a message from nature?
Yeah. No, I think that is amazing. And I'm not a member of LIGO, but I remember that when that announcement came out, it really was amazing. And the fact that it happened so quickly when the experiment was turned on. And that's kind of leads me to my next question, talking about the present, is, there were these decades of planning, but what do you think made LIGO as an experiment, not just the physical experiment itself, but as a scientific group, of close to 1,000 people working towards this, what made it able to succeed so well in making such a detection very quickly, and then doing the science, announcing it within a few months, and kind of shocking the world, as you said.
Yeah, so I think different people you ask will give you slightly different answers to that. But my own sense is that one of the biggest keys to the success of this big scientific collaboration, as you said, 1,000 scientists, one of the keys was common purpose. And that was that we most of us, I'll speak for myself certainly, but most of us understood that each of the pieces or building blocks of the collaboration was critical. So there were the people like me who built the instrument and got it to the sensitivity that was needed. But we could never have done much with that instrument if there wasn't another group of people who took the data that was coming out and matched that data to the astrophysical predictions. And they couldn't have done that without the astrophysical predictions that were being done by theory groups. So these three things, sort of the data analysis and computation, the theory and simulation, and the instrument, all had to come together. And they're rather different communities that don't often even speak the same language. So at the interfaces, there were some very important visionary people that were keeping it all together as well. So I think common purpose. And the other thing that's really important is pretty early on, LIGO joined forces with Virgo, the European gravitational wave detector. And it's easy to think that these should be competitive, but we understood pretty early on that we're better going it together. So there was also very collaborative, and that I think really makes the scientific collaboration more open. People are not guarded and territorial. Not that there wasn't some of that stuff as well. We're by no means perfect. We're humans, but there was more of this sense of common purpose and collaboration because there was no way any one group or sets of groups could do this on their own.
Yeah.
And we happen to like each other. That helps too.
That is fantastic. Within the discoveries that you mentioned two specific events: the first collision that was detected of two black holes, and then the collision of two neutron stars. But LIGO has made additional detections over the last few years, and I was kind of wondering if you can tell us which one of these scientific breakthroughs that LIGO has made so far is your personal favorite.
Yeah, so that's a great question. So I think my personal favorite I already spoke about, which is it's a little bit like the following. The first collision of black holes is kind of like your firstborn child. I mean, you can have other kids and you'll love them as much, but that is the firstborn. You've never had that experience. And then the first collision of neutron stars was really just, it in some ways it eclipses the black hole because it was such an extravaganza, right? There was all this light that came out of it, and so many instruments involved. And so in some ways I that may be my favorite. But on the meantime, there have been other discoveries, and it's a reminder. The very first one was also a reminder of this, but this is a constant reminder to me that when we make a big scientific discovery, we're really just asking the next question. So even with the first collision of black holes, it revealed mysteries. We don't know how nature makes such heavy black holes. We did not expect that. We don't know how these black holes come to be in pairs and orbiting each other. We have some ideas, but we don't know what nature really does. And then some of the exciting discoveries we've had since is, for example, I told you, neutron stars, 1 to 2 solar masses, black holes heavier than 5 solar masses. Well, what's in between the 2 and solar masses and the 5 solar masses? We don't know. But we did make an observation of an object that was in this sort of 2.6 solar mass range. And so is it a neutron star? Is it a black hole? And that's one of the mysteries that more observations, as we make these instruments more precise, will help us to disentangle. And so by now there have been, I think, we're approaching like 80 separate observations of different objects, and there are some patterns, but there are also not enough patterns to say, wow, we figured it out, this is how nature works. It's a little bit like saying if an alien came here to the earth and observed one human and extrapolated what the human species is like, that's what we would be doing if we looked at one black hole pair or one neutron star pair. And so we're still in that process of understanding all the different ways in which nature puts these systems together.
Yeah. And that kind of leads me to kind of the next topic, which is the future. So as you mentioned, the field is just coming into itself and is just starting. And I was kind of wondering, what technological advances that will enable the next generation of detectors are you most excited about? What is kind of the next big thing?
Yeah. So, to answer that question about, what's the next generation of detectors going to do, the first thing you have to answer is, well, what is limiting this generation of detectors? Why can't we do better already? Why can we only measure 10 to the minus 19 meters right now? Why can't we do 10 to the minus 20, 21, etc.? And the answer is quantum mechanics. And so, quantum mechanics governs the motion of the smallest things that we know of, right? Atoms, electrons inside of atoms. And so you will say, well, what does quantum mechanics have to do with LIGO? LIGO's mirrors are, 40 kilograms. They're 2/3 of my mass, and they're big. And but But when they have such tiny motions, 10 to the minus 19 meters of motion, the quantum mechanical jitter of the world disturbs the measurement. And so one of the technologies that we're really working on is trying to do measurements that allow us to get past these quantum limits using special quantum states, entanglement, for example, which is a spooky quantum idea. So there are a whole bunch of technologies that will go into making the future detectors better. But I want to kind of pivot to something that if you ask me, what do I dream of? And I don't think this will happen maybe in my lifetime with these kinds of instruments, but this is the dream. And remember, the universe we see today and understand today came 400 years after Galileo's first telescope. So we have a little bit of time to get there. So what I dream of is the following. If you look at the earliest moments of the universe, we think the universe began in a big bang, and that it began to expand, and all of matter and light was kind of trapped in a soup. And when you look at the earliest light that we can see from the universe, it escaped from this hot soup of matter when the universe was about 400,000 years old. Now, why is that? It's because light interacts with matter. So a nice analogy for this is, imagine you go to a party, and you go to the party with an extrovert. So you say to your friend, okay, I'm ready to leave. And by the time they leave the party, it takes an hour because they stop to say hello and goodbye to everyone. And, it takes a long time. And that's how light was. It bounces off all the different matter, atoms, electrons, etc. And it didn't escape this hot soup until the universe was expanded enough and cool enough, and that was 400,000 years ago. So if you use light to look at the universe, the earliest moments of the universe you can see is 400,000, when it was 400,000 years old. Now, gravitational waves are just the opposite. It's like going to that same party with an introvert, and you tell your friend, I'm ready to leave, and you're kind of lucky if they even go say thank you and goodbye to the host. They're straight out the door, right? And gravitational waves were like that. So they have been streaming towards us from the very earliest moments after the Big Bang. So if you could see gravitational waves from this early universe, these primordial gravitational waves, you are looking at the very earliest moments of the birth of our universe. And that's what I dream about. They're extremely faint, very hard to see, and therefore, our current instruments would have to be almost 1 million times more sensitive to see them. But if you could, you would see the universe when it was 10 to the minus 22 seconds old. And who wouldn't have a good night's sleep dreaming of that? So I'll stop there.
Thank you, Nergis. That's very inspirational. And many thanks for sharing these personal and professional reflections. And now I want to take some questions from the audience, and there are quite a few. So I will try to kind of combine them together. So let's see. We have a question about whether LIGO is permanently turned on, waiting for gravitational waves to be detected.
Yeah, so LIGO is kind of permanently turned on. It goes through periods of many, many months at a time when the instrument is turned on and is just looking out at the whole sky. And then it goes through periods of several months or years at a time when it's turned off for instrument improvements. And we're actually in a turned off phase right now since COVID began, and we've used this time to make instrumental improvements. And every time it comes back from these instrumental improvements, we hope to get something on the order of a 50% to a factor of 2 improvement in sensitivity. And that allows us to look farther into the universe and to see fainter objects. And so it's this constant game of improve the instrument, observe for a while, improve again, observe again. And it's done in coordination with Virgo, and so that we're always trying to do science together.
Another question asks whether having something like LIGO in space would give a different view from what we can see from the Earth.
Yeah, and in fact, there is a concept for not quite LIGO, but a space instrument for gravitational waves called LISA. It's the Laser Interferometer Space Antenna, which has been for a long time, decades now, been under development by NASA and the European Space Agency. And the reason to go into space is actually to measure a different frequency or wavelength of gravitational waves. It's a little bit like here on the Earth, it would be a little bit like having a radio telescope for lower frequency waves. And the reason is that the Earth's vibrations are just too large to overcome when you get to frequencies below a few hertz. And then if you want to make measurements of gravitational waves that are slower than oscillating slower than once per second, you have to get off the planet. And so LISA would look at these lower frequency gravitational waves, and that's very exciting scientifically, because when we think about supermassive black holes, like the black holes at the centers of galaxies, those aren't whipping around at 100 times per second like LIGO or Virgo would see. Those are lumbering around each other, once every few years even. And LISA would be able to see those kinds of collisions. And so a very different set of observations is possible when you go into space. And LISA has, by the way, a launch date of 2034. So it's real, but these things often get delayed.
Yeah. There's a question here. In the introduction, Tomiko mentioned the tension between quantum mechanics and gravitational waves. We have a question from the audience about whether what your thoughts are on this tension and whether there's a way to resolve it, and would gravitational waves play a role in that?
Yeah, so it's a really, really good question. So the tension really is that we don't know how to quantize gravity. So if you start to look at space-time itself on smaller and smaller scales, what will it look like? Will it be, what kind of quantum mechanical foam and fuzz will gravity have? And we don't know how to do that mathematically or conceptually. So that's the tension, that we don't have a quantized theory for gravity. The tension in LIGO between quantum mechanics and gravitational waves is that the jitteriness of quantum mechanics, just the quantum uncertainty principle, introduces of uncertainty in our measurement, and that limits how well we can measure the gravitational wave, whose effect here is tiny. Look, if you were close to the black hole, it would be a whopping big effect. I mean, you wouldn't want to be there because it would be extremely uncomfortable. But if you could be closer, you would, there wouldn't be this fundamental tension. So really, this tension comes in two forms. There's the quantum mechanical jitter disturbs our measurement, and at a more fundamental level, we scientists don't yet know what a quantum theory for gravity is. Now, will LIGO have anything to say about that? Possibly, yes, and it already has. So you can take some putative theory of quantum gravity, and the particle of the quantum of that theory would be a graviton. And by looking at the dispersion, the rate at which the gravitational wave travels through space, you can actually put a limit on the mass of the graviton, and LIGO has done that with all its different observations. And it's a tiny number, but there is a number. So in some ways, we're putting some numerical bounds on a particle when we have no idea what that particle's mass range should be, or if it even should be. Now, personally, I think there will be eventually a graviton. This is just how all of the other forces have unfolded, but we don't know anything about it yet.
And our one final question. When gravitational waves travel through space, do they travel essentially unimpeded, or can matter stop gravitational waves?
Oh, so this is both a blessing and a curse. So the gravitational waves, for the same reason that I told you they're aloof and they're introverts at the party, they really don't interact much with matter. They pass right through objects, and that's one of the things that we're very excited about for gravitational wave astrophysics, because you don't have to worry about what was between you and the source that emitted them. It goes through most everything. So that's wonderful as an astronomer, astrophysics. Wow, you don't have to worry about it. As the instrument builder, it's a terrible headache because it also interacts really weakly with our instrument. And that's part of what makes the measurement so hard. It's such a weak interaction. But I would say, yes, so the gravitational waves, they interact very weakly with matter and with each other.
Great. Well, thank you so much, Nergis, for a really wonderful talk, for telling us so much about gravitational waves, and giving us a view from the inside, from somebody who's worked on this project for so many years and has been instrumental in bringing it to such successful results. So this concludes our program today. I want to thank Nergis again, and the audience for very insightful questions. Today's program has been recorded and will be posted on the Radcliffe website in about a week. For information on upcoming Radcliffe virtual programs, including our upcoming Science Symposium on Artificial Intelligence on October 22nd, or to see videos of past events, please visit www.radcliffe.harvard.edu. Thank you again for joining us today, and take care.